Everybody, my name is Matthew Farrell Beltran, and this is my presentation on Physics Lab 1. So to start, the purpose of this lab was to observe and track the movement of an object traveling in one direction with a constant velocity. So how we experimented this in our group was we had a frictionless cart track and obviously the cart. So we pushed the cart on the track using our hand, and then we had the measuring tape on the track itself to help us measure the distance that the cart traveled. One property that this lab really focuses on is Newton's second law, which is the net force equals mass times net acceleration. So in an instance in which there is a constant velocity, that means that there should be no force acting on an object during its movement. Therefore, by Newton's second law, if there's no force during movement, there will be no acceleration. Moving from Newton's second law to the velocity update, since we know that there's no acceleration in the velocity update, the factor of a times t will cancel out, therefore leaving us with the final velocity equaling the initial velocity. And then for position update, which is the final position is equal to initial position plus the product of velocity times time. Since we know that final and initial velocity are the same, if there's no force during Newton's second law, then we can use either final or initial velocity in our position update formula. And then we can automatically say that in our experiment, our object is going to slow down and therefore now have a constant velocity, and this is most likely due to friction. For our experiment, we had a 400-gram cart as our system. This measurement might not be exact. We simply had to look up the product of the frictionless track and the cart and just go based off what the internet said what the weight of the cart was. So in this experiment, we assumed that friction was negligible and the cart had a constant velocity. And through these assumptions, the only forces actually acting on the cart would be forces in the y direction, which would be gravitational and normal force. These forces are equal in magnitude, just opposite direction. So gravitational force acts downward on the object and normal force acts upwards. Other initial conditions include our initial position, which was negative 0.00170286 meters, and our initial velocity was 3.128 meters per second. For the model comparisons, the blue line represents the predicted motion of our cart with respect to time while assuming a constant velocity, and this predicted motion is calculated through the GlowScript code. And the red line depicts our cart's observed motion with respect to time. This was used, this was calculated using the data we got off Tracker. And if you look really closely at the bottom left portion of the red line, there is a faint, translucent red line of best fit. And you can also see at the top of our graph key that the trend line for the observed position isn't exactly 1, it's 0.999, meaning that the red line isn't exactly straight. And then the difference in these slopes confirms that our cart did not display a constant velocity. If our cart did display a constant velocity during the experiment, then it would have had the same slope as the predicted blue line. And here's the GlowScript code on the right where the picture is. That's the main section on which I changed the code. And some of the factors edited were the mass of the car. I changed it to 0.4 to represent 0.4 kilograms or 400 grams. I also, in the first balled up pause condition, I changed the initial x position, and balled up vel, I also changed the initial x velocity. Since this experiment focuses on just one directional horizontal movement, I only had to change the x factors for both position and velocity. And delta t was calculated since our video recording on Tracker only lasted half of a second, and there's 15 steps that we use to calculate the distance. That's how we calculate our delta t. And we also changed the time maximum to being less than 0.5 seconds, since again our video only lasted 0.5 seconds. Since net force is 0, all the factors of the net force vector are 0, and then the ball velocity code remains constant since velocity in real life, or well, at least in this scenario, remains constant. And the position is updated by multiplying it by delta t. So for our discussion questions, First question is, what if you analyze your video data on Tracker and you made the choice of changing the orientation of the axes? So simply by changing from the positive x direction to the negative x direction, that would just change our position and velocity values by a factor of -1, or simply just flip the signs. And what does the overall conclusions of the experiment mean? This kind of shows that since our car did eventually slow down, we cannot claim that our object had a constant velocity nor zero net force. And in our experiment, the factors that caused our car to slow down and experience some sort of force were friction and air resistance, and these forces acted in the opposite direction of our car's movement. In conclusion, like I said earlier, since there were forces acting against the direction of the cart's movement, our cart did not display a constant velocity. This difference is clearly shown in the difference between the observed and prediction motion slopes. And like I said earlier, had our cart had a constant velocity, both slopes would have matched. Therefore, our observed slope would have matched the predicted slope from GlowScript. Some sources of error that might be possible in our experiment were friction between the cart's wheels and the track surface, or also air resistance, and we also could have just had a human error and miscalculations on the tracker application. Thank you for your time.